Okay, can you hear me? Good. So I've done a bunch of talks in my time, but this is the first time I have this little friend here. It's very exciting. So I want to spend the next 30 minutes talking a little bit about my kind of learnings and observations about using machine learning in production. But first, I want to just tell you why I think I have some authority on the topic. So, my name is Inmar. I'm a proud Canadian. I'm also a recovering Israeli, so I'm one of these people who went to the army and can very politely kill you. But really, so I can use a rifle, but what I did in the army was software development. This is kind of where I started my journey in Israel. It's where a lot of the technology starts from. And then when I did my undergraduate degree, I took a machine learning course, and I got really excited about it. So I moved here to Toronto, went to U of T, did a PhD in machine learning, and then afterwards decided to go to industry, first as an individual contributor, or research scientist, or whatever you want to call it, and later on managing and building machine learning research and engineering teams. And for the last little while, since September, I've been at a company called Kindred, where we're building exciting robots at the intersection of robotics and AI. So it's been a completely insane yet tremendously satisfying journey so far. So I want to talk about three things today. The first is what I think machine learning is, and maybe do a little bit of a cleanup of the terminology and the capabilities of machine learning algorithms. I want to talk about what can machine learning do for you. So in your organizations, if you're not a core AI company, how can you still use it? Go through some examples, talk about what can and cannot be done with machine learning. And finally, I want to talk a little bit about how do you hire, recruit for machine learning teams, and who are the people you actually need to have if you're trying to do something like that. Okay, so let's get started. So first of all, let's talk about AI. So this is something that was, this is a sentence that I quite like. As soon as it works, no one calls it AI anymore. It was coined by John McCarthy, who was one of the godfathers of AI. He coined the term AI himself. He was also an amazing computer scientist who invented a lot of other things like Lisp and garbage collection and so on. And AI is really the study within computer science typically of the attempt to automate intelligent behavior. And given that definition, it doesn't actually prescribe in any way or form how to go about it. You can do it by writing down a whole bunch of rules. You can do it by representing knowledge between entities. You can do it by having some form of an exhaustive search over possibilities. It's a very vague and broad definition of how to go about creating automated versions of intelligence. Machine learning is the computational approaches and methodologies for making sense of data. And the term learning here indicates that we're actually going to use data. So it is a prescription for how you're going to go about generating intelligence. You're going to learn from examples. You're going to look at data. And it's very fundamental for the notion of machine learning. And it means that we are relying on an existing information, on existing examples as a way to generate intelligence. And we're building something that over time improves and gets better. So from that, let's talk about a specific example. So a pretty typical task in machine learning is a supervised learning task, and more specifically classification. So we want to build an algorithm that can distinguish it between images of dogs and cats. And in order to do that, rather than the traditional software engineering methodology, which would be, we write down some sort of if-else statements describing a cat and describing a dog, we're not going to do that. We're going to take a whole bunch of examples of dogs and cats, and we're going to push it some machinery, and the output will basically be something that can now, given a new image, tell us whether it's a cat or a dog. So we can say that machine learning, the way that I'm thinking about it, is basically a subdomain within the broader domain of AI. And I also want to talk a little bit about deep learning, because it's definitely a term that's been making the headlines recently. So deep learning is a methodology within machine learning, and specifically it's borrowing a lot of, let's say, intuition or ideas from how the brain works, and particularly how the cortex works, in the following sense. In the brain, we have neurons, and the neurons receive information. They receive electrical signals, and then they combine them in some sort of way, and then they decide whether or not to emit an outgoing signal, so a spike. And in the cortex, what neuroscientists observe is that there is this notion of a layer of neurons that does its computation and then transfers the information to another layer and so on. So this notion of neurons that can do computations was borrowed into computer science in a very simplified version, and you can show that it is a mathematical function and it is a universal approximation, so you can approximate any function with it. And these were the first artificial neural networks that have been around for a long time, but people observed that the shallow neural networks, the one that didn't have a lot of layers, weren't really producing interesting results, and the notion for a long time was that you would actually need to have these series of layers in order to get really good results, but no one really knew how to train them. So that was the problem for many, many years. This is like by no stretch of the imagination a new technology, and why we're seeing so much talk about deep learning is that in recent years, and I'll talk about why in a minute, we're finally able to train these deep neural networks, and that's the source of the term deep learning. Okay, so this is the mental model that I have about all of these terms that get thrown around. And just to make a comment, so coming from machine learning, for a while I was trying to tell people who were talking about AI, no, you're talking about machine learning. Everything that's happening is machine learning, but I've kind of given up. So I do use the terms interchangeably now, even though every time, I cry a little inside. But most of what you're seeing, most of what people are talking about when they're talking about AI is machine learning and probably a lot of deep learning in it. So why do we see this proliferation of machine learning into so much of technology? So the first big reason is data, right? So there is this Chinese adage that says there is no cloud, it's someone else's computer. And so we are constantly loading our data into a bunch of computers that belong to Google and Facebook and all of these giants that provide us with so many services that make our lives easier, but they get all the data. And as I mentioned, machine learning kind of relies on this notion of having data to learn from. And so with this proliferation of data, with the fact that each one of us is carrying around basically a pretty powerful computer with a whole bunch of sensors that is constantly sending off information about any activity we choose to take, whether it's our location, what we're choosing to watch on YouTube, what we're choosing to listen to, where are we tapping, and of course the same for desktop or laptop computers. Suddenly we have companies and we have entities that have amassed enough data to properly train these algorithms that for many years were available but very data starved. The second important thing is if you're going to have so much data, you're going to have to try to compute through it, to crunch through it. And again, that was a limitation, but hardware is becoming so much cheaper and able to provide us computation that weren't there before. So the most important example is, of course, GPUs, graphical processing units. I'm sure you all know of them. They started out as a tool for the gaming community, really, because they are highly parallelized. They allow you to do highly parallelizable computations. When you're rendering pixels, each pixel can be computed independently, but it turns out that these are actually extremely useful for computing the results from machine learning algorithms, and in particular, things like neural networks. And so that was another important technological advance that allowed for machine learning algorithms to become commonplace. And then given these two things, given the existence of data in large amounts and cheap computing, which is, so I mentioned GPUs and so on, but also the fact that we now have cloud services, we can spin up machines in a matter of minutes, we have access to GPUs that we don't need to buy ourselves and so on, people have started building a lot of infrastructure around it, right? So there's a lot of open source communities that are building really powerful tools to allow us to crunch through these amounts of data, because there are engineering challenges in going through the data, and it needed some rethinking about how we're doing certain operations, how we're parallelizing it efficiently, how we're collecting the data, and so on. So over the last, I would say, decade or so, people have been building more and more off-the-shelf tools that anyone can use very quickly to run machine learning algorithms on large amount of data on very large computing services. And that's important because 10 years ago, if you wanted to run some sort of a machine learning algorithm, you basically had to sit down and write it yourself and implement it yourself. And they're typically algorithms that have a lot of mathematics in them, so you needed to be really careful, very easy to create bugs, and so on. Whereas now, if you want to use one of these algorithms, you will find within seconds an implementation in any language you can think of, and then not just the implementation of the core algorithm, the layer above it that allows you to run experiments and measure and look at metrics and so on, and then the layer above it that allows you to parallelize it and implement it at scale. So all of these things are now solved problems to a large extent. So together, that makes it, that brings us to a place where it's really, it's quite straightforward to start using machine learning in production. Okay, so let's talk a little bit about machine learning in the context of what it is that can be done for, let's say, an average company or a business. And I'll go through some historical examples, kind of taking us to today, and the first example that I think was quite relevant for everyone is, early in the 90s, we all started using emails, and it was really nice. We could contact people and be in touch with our friends and colleagues. But it was also an opportunity for people to, send you a lot of crap. So we needed to do something about it, right? And so along came spam detectors. And spam detectors are basically one of the first instances of commercial applications of machine learning. You would take a bunch of data, so that would be examples of emails that are real emails, so ham in the technical jargon, and emails that are actually spam. And then you would put them into this machine learning apparatus, and it will create a functionality that allows you, given a new email, to say whether it was ham or spam. And as the user was also giving signals, so the user would sometimes go into their spam folder and say, well, this is actually not a spam email, or in their inbox they would say, this is an email that is a form of spam. The algorithm would be able to continuously improve. Fast forward a few more years, we started seeing face detection, say, on digital cameras. So remember, when people still bought digital cameras that were, the click and shoot, it would draw like these little squares around people's faces, and that will tell you that some onboard algorithm had recognized that there is a face in this area. And now I don't think that cameras even bother doing it, because even though they do detect the faces, they just use it for things like autofocusing and whatnot. And this is another example of early use of a machine learning algorithm. The next step for that was not just face detection, but face recognition. So now given that we know who someone is, we can detect that same person in a bunch of different images and say these are all the same person. One of the recent exciting advances in machine learning is machine translation. So basically the idea that we put as input a sentence and we get as output the same sentence in a different language. And this is really getting into stuff that's quite exciting because we're pretty close to having something like the Babelfish, some device that we can stick in our ear and then it will translate into any language. And this is kind of an example that I'm particularly fond of because back at the day at Kobo, I built one of these systems. So this was a porn detection system. So Kobo had a lot of different books, and some of them were pornographic, and we built a system that would allow us to detect which ones had pornographic content. So the input there was the text of the book, and the output was some indication of whether or not we thought it was pornographic. And it was a pretty weird time in my life where I had a folder on my desktop called Porn at Work, and that's exactly what it was. Okay, so now, a question that I think comes to mind for people who don't have a background in machine learning is, okay, there is so much hype around it. How do I know what's possible to do with machine learning? How do I differentiate the hype from reality? How do I call bullshit on some things that people are saying, oh, we're using AI, we're using machine learning to solve it? So I sometimes give talk where I try to go a little bit under the hood and explain the mathematics and the intuition. We don't really have time to do it today, but I was thinking about this crowd in particular and something that I can say about it to you. And if there's one thing that everyone here probably understands really well, it's the notion of a function, right? A software engineering function. And it's important to remember that a machine learning algorithm, at the end of the day, is a function. And what does it mean? It means that it takes very specific input, okay? The input has to be well-defined. It does some operation on the input, and it produces an output. The output is also well-defined. As I mentioned before, the process is not, the traditional approach would be for some engineer who got the spec to sit down and implement this relationship between the input and the output. In machine learning, instead of doing that, we provide a whole lot of examples that map the input to the output, and we push it through some mathematical machinery that learns how to automatically generate this relationship. So it's a software engineering type of function, but it's also a mathematical type of function. And really what's going under the hood is that this function has some parameters, and all the machine learning algorithm is trying to do is find the right settings for these parameters so that the mapping between the examples it sees are as close as possible to, the mapping that it generates are as close as possible to the example it sees. But all of that doesn't matter. What matters is understanding this notion of this is just a function. So if anyone comes to you and tells you a story about, what amazing AI they're doing, as an engineer, you should be able to start probing. Even if you don't understand the algorithm, you should be able to start probing and say, okay, explain to me, what are the inputs? What is the data set they're using to generate the relationship between the input and the outputs? And what are the outputs? And these things should be fairly narrow and specific. It's not going to be some nebulous, oh, we push all of the user data and out comes something, right? It's got to be quite defined. And maybe it's a complicated process. Maybe it's not a single function. Maybe it's a chain of functions, and you chain the output to something else, and it becomes quite complex. But that's not machine learning. That's just software engineering. All of you have built constructions where you're using a lot of functions and interact in complex ways. Nevertheless, you are able to explain each one of these functions individually. So that's one way to try and kind of probe at things. And the one thing that's not going to happen, and you can typically call bullshit on, is anyone who tells you, yes, we throw in all the data and out come these amazing insights about our users. That's just not a thing, right? In order to provide insight, someone has to sit there and define precisely what is the insight we're looking for, what is the thing that we're trying to predict, what are the inputs, what are the outputs, what is the data we're using to train this relationship, how are we representing the input in a way that is computer readable. And just to caveat a little bit what I'm saying, of course, not all machine learning algorithms are supervised learning. There are generative algorithms and so on, but there's still the notion of there is an input and there is a well-defined output, and this should be arrays of numbers or a representation of a file of text, a representation of an image, of a sound file, and so on, something that is well-defined, and again, the output should be something well-defined. So I hope that maybe helps a little bit in trying to kind of demystify the magic. So now I'm going to flip the question on its head. What can you do for machine learning? And what I mean by that is, if you're going to do it, what are some observations that I've had about best practices in terms of, or good practices, let's say, in terms of engineering and how to think about it? So the first thing that I would suggest is start simple, okay? If you want to implement some capability using a machine learning algorithm, start with the simplest thing you can think of, or that your data scientist can think of, and see what happens. And the reason I advocate for that is, even if you know that the real scope of the problem is quite a bit more complicated, and there are all these 10 different things that you'd really like to do, seeing the first iteration of an algorithm allows you to actually know where to go next. It allows you to see, okay, I've used a simple algorithm and it doesn't work on all of these cases, and now I can probe why isn't it working, and from there I can think about what are the changes I need to make in order to make it work better. And these changes are not necessarily a more complicated algorithm. Sometimes it just means that my data coverage is not good enough. I don't have enough examples of negative types of data. Maybe it means that my features that are basically, the features are how I map the real nebulous data that I'm taking as input into some array of numbers. The features I've selected are not the right features, and I can play around with that. The other thing that it will give you is probably immediate value. So let's say that you're trying to put together a recommendation system. And there are quite complex recommendation systems nowadays, and they require a lot of time and effort, but you can also spin something out that is very quick to implement. Basically use some existing off-the-shelf recommendation engine that uses some very simple features, and immediately you'll start seeing the gains from that system, because not having one is obviously not as good as having one. So even if over time you will start improving on it and making it more complex and get to where you originally wanted to go, you'll see these benefits right off the bat. And it's often the case that the first simple variant gets you a big chunk of the way. And then everything that you do on top of it are small improvements and small incrementations that take longer and longer to arrive to. So if you're trying to jump to the end result with the complex algorithm right off the bat, you will be spending a lot of time trying to put it together. And you might not even get there. Okay, the second observation that I want to share with you is about thinking about it in terms of products or services. You want to use machine learning to push out services. You don't want to use, in my opinion, machine learning to do some interesting analysis and bring it to a bunch of marketing and sales people and business people who are going to look at it and make decisions. So instead of a decision support tool, you want to use it for something that is actionable and a product. So let me give you an example. Maybe you have some sort of email cadence that you send to your customers for sales, right? Like you want to show what kind of products you have on sale. And probably someone from the CRM group is asking, what is the best time of day to send people emails? And maybe they'll go and ask the data scientist to do some sort of an analysis with a predictive model and complicated tools to say, let's break our population into segments and use some demographic information and whatnot to understand for each demographic what is the best time, and then for each of them we'll create an email and so on and so forth. And so the data scientists will present the results, and then a bunch of people are going to look at it and make some decisions and then use it to send emails. But really, the machine learning way of thinking about it is we're going to make do with all of the people in the middle, and all we really want to do is generate some sort of a system that for each individual user personalizes the experience and just automatically detects what is the right time to send them a particular email based on their user behavior and previous history. So it's a different mindset. We're not thinking about it as data as tools for decision making. We're thinking about it as how do I actually get something out without a man in the middle or person in the middle. The next point is it's very worthwhile to invest in good engineering pipelines. And by that I mean you need tooling, so tooling is an important issue, to allow you to do all sorts of things, and especially to allow you to iterate through different algorithms quickly and replace existing algorithms with other ones, compare algorithms with one another. And if you don't take the time to build that system, which is, it's an engineering system, it's not a machine learning thing, it's not a machine learning expertise, it's going to be very difficult for you to move forward with improving algorithms, with adding new algorithms and so on. Thinking about it as an engineering problem, how do I create this part of my pipeline, maybe using the notion of microservice or something like that, where it's easier to replace what's happening in the background, and it's completely decoupled from your main production pipeline, and so on. And one good example for that would be in the context of what's called A/B testing. So a lot of times, maybe you have an algorithm that's already running, let's say a recommendation system, and you want to try another one. The common way of approaching it would be to divide your user base into two and compare between them. Now, why would you want to try the second algorithm? Probably because you did some offline analysis, which looks at the function that the machine learning algorithm is trying to solve and looks at some metrics that have to do with this function. And the metrics are what is used to optimize the machine learning algorithm, but they're not necessarily tied to the metrics that your business cares about, which is things like, how many users are coming to the website or how much money am I making from them. So it's not typically optimizing for that. So at the end of the day, even if your offline evaluation of an algorithm seems to indicate that it's better than the current one, what you really want to do is run them one against the other and make sure that in reality, for your business metrics, one of them is better than the other, and for that you need to set up an infrastructure to allow you to do that, to run these types of tests. Okay. And then the last thing I want to touch upon is hiring and building groups for doing machine learning. So it's a relatively new area, and there are a lot of different names and different titles. You have your machine learning researcher, machine learning engineer, data scientist, data engineer, and so on. Different people have different ideas about what that means. And I think one of the notions, one of the kind of myth, I would say, that I'd like to debunk is the idea that in order to do machine learning in my company, I have to hire a machine learning PhD. And I feel like I can, I'm allowed to say things about why you don't need a machine learning PhD because I am one. So I'm not actually, I'm offending myself in a way. So the problem with hiring a machine learning PhD is that it's probably not what you need. For the following reason. The first thing is that they're going to be extremely expensive. They're going to come out of academia with expectations of doing what they did in academia, which is basically concentrating on pushing the envelope, pushing the state of the art on what's happening in machine learning, which means they want to do interesting, complex algorithms rather than trying as I said, the simplest thing for a variety of problems that you probably have and probably want to use machine learning for. So Facebook and Google and other companies have created these hubs that allow these types of researchers to go and continue to basically do very academic work surrounded by their peers, so working with a lot of people from the field, having to worry very little about the engineering infrastructure because it's all kind of prepared by the best engineers in the world for them to just use. And they have the academic mindset, so they want to go down every rabbit hole. They want to continue to explore anything that they don't quite understand and so on. And that's typically not what you actually want. What you want is someone who is very practically minded, who wants to try to get results fast, who want to try starting with something simple and only evolve as needed. And that's not what you're going to get. So a lot of times there is this frustration that gets created when you do end up hiring someone like that. And that's true, of course, unless your core business is AI, or machine learning, unless you're really sure that the problem you're trying to solve is one that doesn't really have an existing solution and is basically an academic, scientific problem. So yeah, in that case, of course, go ahead and try to hire these people. Okay, but then the problem is, maybe you have an organization and maybe you have a sense that AI could probably be useful, but you don't know where to start. And so you say machine learning person, machine learning PhD has all the knowledge of the field and the abilities and the algorithm and so on. So basically what you're looking for in that person is not their technical ability to develop new algorithms, it's the expertise that you're going after, right? So in terms of expertise, there are other people with that type of expertise. So for instance, people who've been doing it for a few years. So this is very similar to typical engineering. You're hiring a senior engineer because you want someone who's already done it before and seen it. But these would be people that are much more production-minded. There are a lot of people who maybe have a master's degree in machine learning or maybe a PhD in some other area. So a PhD is basically just like a stamp that you can go and learn stuff that you don't know and do it at a reasonable rate, right? So a lot of people from similar industries that get interested in machine learning will go and study it, and that will often be also a good opportunity for hiring. And I think most importantly, there are a lot of engineers that are super interested in it and are really willing to take the time and go and learn it on their own and do online courses and play around with all the platforms and tutorials that are out there. And there's probably a couple of engineers like that in your company that are really keen and letting them run with it and try a few simple things and figure out themselves how to use it is probably a good idea, and they'll be really happy and they will usually give you very good results. But you do have to worry about the engineering infrastructure. So even if someone running groups that do have these machine learning PhDs, 95% of the work is going to be engineering. Okay? You're going to spend most of your time on building the pipelines, massaging the data, storing the data, retrieving the data, making sure that the output goes somewhere in a reasonable amount of time. And so it's really important that as you're planning to do something like that, you have someone who's an expert in the systems engineering side of things, who's really thinking hard about how are we going to build the infrastructure to allow us to really make use of the people who are doing the more focused machine learning work. And what I've seen when people don't pay enough of attention to building the infrastructure and putting it in place, you get several phenomena. So one of them is like the group of data scientists that are sitting somewhere in a room and they have some dumps of the data, and they're showing you really exciting things about what they can do in the data, but it doesn't connect, right? It never actually gets into production because they're doing it in their own little world that isn't connected by any engineering pipeline, and no one's put it in place, and they don't know how to do it because maybe, they are this PhD in physics who knows how to write code and knows the machine learning algorithm, but doesn't really know much about system engineering. Or the other thing that can happen is you have a very clunky, leaky pipeline that has been put in place, and it's really, really hard to work with, it's really hard to replace, and it just kind of sits there and rots away over time because it's really hard to replace it with anything else. You didn't take the time to do it properly. So I think that's it for me. I want to thank you for listening, and I'm happy to take any questions.
All right. Thank you very much. Inmar, I think I speak for everyone when I say, please don't hurt me. Okay, where are the questions? No questions?
Oh, wow.
Oh, okay, we're going back here.
Not to make light of it, but I was curious how you got all the visuals for your slides.
Actually, it's something I wanted to mention. So shout out to my friend Luca Lee. His name is over there in the corner, who did the designs for me. He's great at doing things like that, and it's been fun to work with him on slides. It's a new thing for me.
Awesome. What are the most exciting examples? I know you've given a few examples, translation and others. What are the most kind of exciting or unexpected examples of how you've seen some of the deep learning applied?
So I think the exciting ones are ones that we're not quite using, so they're more like the wow factor, but I think we're going to start using them at some point, which is generative models. So a model that can basically generate an image of, say, a person, right? So your input would be basically text describing an image, and the output would be an image that looks like a photo that is generated by this type of model. And historically, we were working on the other direction, so taking an image, how do you extract a sentence that describes the image? And that in itself was an interesting and difficult machine learning problem, but the fact that we can now go the other way is quite, it kind of makes you wonder about how it would affect things like film production, right?
All right, we got more questions, okay.
Thanks. Can you talk a little bit about time series, what's happening? Historically, there's been a lot on natural language processing, image processing, but there's a lot to be talked and done about time series data, IoT that creates lots of streams of data.
Yeah, so there is a line of algorithms that use deep learning like LSTMs. So basically, they're looking at some historical information and able to retain some sort of memory. And in general, there is this notion of, in deep learning, we've created something that is sort of like a brain. So people don't like using that analogy, but it does have this notion of computations in this neural network type of way. And if we compare it back to the analogy of where we started from, it doesn't really have a notion of memory. It doesn't really have a notion of short-term memory and long-term memory. So, so people have been working on algorithms to try and incorporate that type of information. And they typically work quite well for things that have a notion of time dependency. So for example, in language translation, you need to remember what you've been doing before.
So Inmar, I think your 95% of your time is going to be spent on the pipes is very true. One of the challenges I've seen is everyone you hire is going to have an opinion on what pipe color you should have because it's a bit of the Wild West out there. So I don't know if you can answer this, but could you give us some tips on like technologies that you think are at like, that are like you should build on, like those pipes should be built with these things first because they're settling a bit more. Because we're going to hire people and they're like buzzword bingo, right? Mm-hmm. So yeah, just do you have an opinion on what kind of technology that? is
Not-
maybe mature a bit more, that
yeah,
you've seen
not
have been like
specific-
safe to bet on your first version?
Yeah, well, okay, a lot of people use Spark, for example. I think it's fair to say that this is a pretty mature technology that's useful. Definitely for data storage, a lot of people use AWS. You need to use some large-scale key value system, and for that you can pick your favorite. I mean, I think, again, it becomes like more of an engineering thing. One thing I would say, which is at a higher level of abstraction, is this idea of trying to decouple it, trying to think about it. I think the analogy of a microservice was really useful for us at Kobo. So basically every service is kind of a thing on its own that you talk to through an API, and you can always very easily modify at the back. So I don't know if it gives you a good answer, but that's how I think about it.
Shalom. What's your opinion of hosted machine learning systems such as Google's and Amazon for using specifically for early stage companies that are getting into machine learning?
Generally good. So do you have more that you want to ask about in terms of security?
Should
like, what
we
are the
invest
considerations?
in creating the infrastructure ourselves, or go ahead and try using hosted infrastructure where we don't have to worry about the engineering aspect, just prove the concept and move on once we get satisfactory results?
Yeah, I'm very much pro using these existing systems and cutting down as much as you can from having to buy the servers and maintain the servers and optimize their performance and so on. The very, very, very early stages, if you don't have massive amounts of data, is stuff that you can probably do on your data scientist laptop. So maybe super early stages you don't need that. But then if you want to build some, if you're looking at building a product, I would definitely recommend using cloud-based services. Yeah.
I have a question about, let's say you're just in the stage where you're trying to figure out how to do your example of porn, not porn, and you're trying to potentially, let's say you don't have the machine learning experience in-house yet, and you kind of want to decide of whether to go with a rules-based engine of like looking for certain keywords or certain types of sentences, or you're going to do a machine learning approach, and you have certain deadlines to hit. Would you recommend to actually start out the gate with a machine learning approach, or to do that later in a comparative algorithm?
It depends a little bit on how useful you think a rule-based system is going to be and how much effort the machine learning work is going to be. So in the example of the porn classifier, it was obvious that there is no real good use case for the rule-based system because it was so simple to just push it through an existing pipeline with existing technologies and existing packages. So I wouldn't have tried spending time on trying to decipher what kind of rules to introduce. And it would have also been a little annoying, I think, in that particular case. And generally speaking, of course, I mean, I am a machine learning person, and I've seen how the like algorithms that rely on data are often, or almost always, better than handcrafted things or things that are based on. One of the things we saw at Kobo again and again and again is that the domain expertise of people who understand about books was never really competitive if you just throw a machine learning algorithm with the right data and test your results. So we always did this A/B testing, and it was always the case that automated procedures using machine learning performed better than the expert type approaches. Not always. I mean, there are specific examples where it's just very hard, like the cold start problem, right? If you don't have any data, basically, of course, the machine learning algorithm is not going to help, and you can definitely rely on expert. But if you have a system that's kind of like a pipeline with existing data and so on, then the automated approaches definitely work well.
So just a comment before I ask my question. If you're going to use cloud-based AI machine learnings, just be aware of some of the rules associated with who owns the data and who owns the model after that fact. So I just going to put a caution out there. At least ask some questions. But my question actually is, I'm curious, you started, or you were introduced as you do a lot of mentoring around AI and machine learning, and I'd be curious sort of what and how you're doing that.
So I do mentoring not necessarily in the context of machine learning. I personally feel that one of the ways in which I can contribute to diversity is by meeting and talking to young women who are kind of starting their technical career, and often they are undergraduate students or even high school students, so it's not in the context of machine learning. I am also involved in an organization called Women in Machine Learning, so we've been around for a decade now. And it's an academic organization, or it's mostly started as an academic organization. We run an annual workshop that's co-hosted with NIPS, the big machine learning academic conference, where over the years we've seen more and more women kind of attend it, and they get a chance to present their work and so on. And then I also do sort of career path types of panels and so on, mostly for young people who are kind of looking at where they want to go in their career. And then there's usually the phase where we sit on the stage and talk, but afterwards people will typically come and talk to me and ask me about getting into the field and what is useful, what do I look like, what do I look at when I screen resumes and so on.
Okay, any more? All right, let's hear it one more time for Inmar. Thank you very much. Wonderful.